Welcome to the next generation of 3D printing. Get ready, because what you're about to see is not available on any commercially available desktop 3D printer. Until now. Unlocking all kinds of material combinations that have never been seen before, we are proud to show you TriFlex, the first ever triple independent extruder 3D printer, designed specifically to print 3 materials all in the same print. We were requested to build a 3D printer that can build 3 materials on a print with at least 200 by 200 millimeters in build area, and the bed must be heated with the intention of printing soft robotic actuators. The print resolution was specified to be equal to or better than the resolution of other desktop machines. Soft actuators require highly complicated geometry that cannot be easily manufactured. They require very flexible, rubbery material that can inflate and deflate with differences in air pressure. 3D printing this kind of part on a normal 3D printer poses a challenge because complicated overhanging structures and internal cavities need special dissolvable support material, and without it, there will be significant losses in quality. We solved that problem by outfitting one of our nozzles with a dissolvable material called PVA, which is a material commonly found in school glue. This material can be printed like any other, and it is used as a support layer that allows us to print steep overhanging features with impeccable quality. This support layer is then dissolved away in water, leaving a perfect part. Another core feature is the ability to print rigid structures around or inside a flexible part. This can be used to give structure to an otherwise flexible mechanism, just like a skeleton. Many dual extrusion 3D printers share one nozzle, and they can only use chemically similar materials, such as different colors of the same plastic, so rigid and flexible materials usually aren't able to be printed in the same print. Yet again, we solved that problem by simply adding another nozzle to our printer. 3D printed soft actuators require custom machine because when printing complex flexible parts with rigid skeletons, there is a distinct lack of options on the 3D printing marketplace. There are dual extrusion machines that can print either flexible or rigid, along with a dissolvable support, and there are triple extruder machines, but they are limited to the same material and they can only do 3 different colors. Additionally, flexible materials require a lot more care when printing, so normal extruders just won't produce good results. We'll get back to this later. Now, it wasn't as easy as simply slapping on a nozzle and calling it a day. This kind of 3D printer is highly custom and was only possible due to many hours of design, building, calibration, and testing. We didn't feel like reinventing the wheel, so instead of creating a new 3D printer from scratch, we modified the existing CR10 V2 from Creality. This machine has a large build volume of 300 by 300 by 400 millimeters, and it features dual Z-axis lead screws, which are necessary to support our heavy X-axis assembly. It also has a rigid, triangulated frame which minimizes vibrations, especially for all tall prints. Our hardware modification was a complete rework to the X-axis to feature 3 independent stepper motors, which control the X-axis motion of the 3 extruders. We mounted each hot end to a water jet cut aluminum plate, and we had a custom mount machined for the central Flexion extruder. We also designed and 3D printed custom mounts for the stepper motors and belt pulleys. The rest of the parts used in this build were off the shelf. To go into more detail on our final design, our central extruder is the Flexion extruder, and it was designed by the inventor of NinjaFlex filament, which is a flexible printing material. Flexion is specifically designed for printing flexible materials and features a novel cam-style tension adjustment wheel as well as a brush to constantly clean out the extruder teeth. It also guides the filament perfectly, leaving no chance of buckling anywhere along the filament path. This results in a very reliable extruder that has completed 36-hour-long prints without a single issue. The other 2 extruders are essentially equivalent and can both print PLA or PVA, or most other common printing materials. And if desired, the printer can be used as a 3-color printer, where all colors are the same material. We also completely rewired the printer. We changed the controller board to the Duet 2 Wi-Fi with the DuX5 expansion, and we did this because we needed our printer to have 9 stepper motors, but the original board that the printer came with only supported 5. The Duet 2 is designed for custom 3D printers, and there are many options available when setting the firmware. This allowed us to create custom tool changing macros, which are special commands for each of the 3 extruders, to ensure that they never crash or interfere with each other during printing. We mounted some spool holders above the printer and added the 3rd extruder motor onto the top of the crossrail. And all of this combines to form the TriFlex. So things never work out at first. It took many hours of troubleshooting before the first print would start properly. Oh god. And then after the printer started moving as we expected, it took multiple rounds of calibration to ensure that the nozzles would perfectly share the same coordinate system. The first thing to do was calibrate X, Y, and Z dimensional accuracy, and this was straightforward, because we used the same hardware as the CR10 V2 on the X-axis, so we just copied the calibration values from the CR10 firmware into the Duet firmware. We then verified these values by printing a 20mm cube and measuring each side with calipers. And then we had to calibrate the nozzle offsets. All of the nozzle offsets were calibrated by an initial rough guess, and then we measured the deviation between the actual and expected position to fine-tune each tool head so they all aligned. When all 3 tool heads were calibrated on every axis, we were ready to begin the real prints. The model we started with is the infamous Benchy. It is a boat that is challenging for 3D printers and has every kind of difficult feature. We use these features to identify flaws in print quality. As you can see, we did multiple trials, and each time we found improvements that could be made. Starting from a blobby, stringy mess, we first improved the tool change routine to be a lot quicker, to reduce the amount of oozing. Then during the second print, the black filament snapped while printing, so we added strain relief to the filament path to reduce the chance of material breaking before it got to the nozzle. Our final Benchy was a success, so we moved on to the next trials. The next test was to see if the 3D printer could actually create a functional soft actuator. The initial results are promising as the TPU bonded very well to the PLA, and it has a high degree of flexibility. You can see the internal cavities that are there to allow pressurization. Unfortunately, the printed model was not airtight, and so we couldn't pressurize it, but we expect this is because the TPU was slightly under extruding, so small gaps were appearing. There's also the possibility of applying a flexible coating to the final print, which should fill any small holes. We also suspect that we need to use a softer TPU to get proper inflation. So this TPU that we're using now has a hardness of 95A, but there are materials as soft as 60A, which is significantly softer. And we have the proper hardware to print it to because we have the Flexion extruder. Due to time and budget constraints, we weren't able to test these. Moving on, our third test was a stress test that involved all 3 materials: flexible TPU in gray, rigid PLA in black, and dissolvable PVA, which is pale yellow. This print is extremely challenging because it requires complex internal support structures, as well as accurate alignment of all 3 nozzles. As you can see, the print completed successfully without any major flaws, taking 36 hours in total to complete. There are some issues with stringing and oozing, but this is because the printing parameters still need some fine-tuning. The PVA support was easy to remove, and it left very smooth overhangs, and even the complicated internal support structure was possible to fully remove after soaking in water at 50 degrees Celsius for 4 hours. This dissolved the support interface and made it easy to remove the internal PLA supports. Our final test is the most complicated, and this is a model of the very cool and very rare tiger tree frog, which has a maze-like structure on its skin, and it's an exceedingly complicated print, requiring hundreds of thousands of lines of G-code to produce. And yet, TriFlex was able to successfully print the model with exceptional quality. As you can see, there were some whisper-thin strings on the printed part, but they were easy to remove during post-processing. We would have liked to print more soft actuator models, but there were no openly available files to print, and so these stress tests should demonstrate that our printer is capable of printing essentially anything, no matter how complicated. Although we were very happy with our device, there is still room for improvement. The print settings still need to be fine-tuned to reduce stringing, and we would like to see how a softer TPU behaves with the Flexion extruder. The printing speed and tool-changing G-code can also be optimized to make prints quicker. In terms of maintenance, just like any 3D printer, it's important to make sure belts are tight, no screws are loose, and the bed is clean. The fans and the motion system should be free from debris, and the nozzles should be replaced every 300 print hours or so. The G-code generation process, called slicing, was fairly involved to set up. We decided to use Cura because it's a free, open source, and well-documented piece of software. And slicing the print for 3 materials requires some knowledge of slicers, but we've created a profile that can be imported into Cura, which will have all the necessary configurations set up already. Since it's out of scope for this video, we've just created a user manual that explains this process in much more detail. This was a very challenging but enjoyable project, and we learned a lot about 3D printers along the way. We'd like to thank the professors at UBC for giving us guidance, and we'd like to thank you for watching this till the end. This was Team 16, TriFlex. Thanks for watching.